Myself Pawan Gupta, roll number 2015010446. In this video, I will talk about the stretching of protein in vacuum by stimulating it in VMD and NAMD. Also, I will compare the PMFs of the experiment using Jarzynski's equality. I hope you will like the video.
I will discuss about the science project protein simulation using VMD and NAMD. So the protein given to me is 3AHA_B.PDB. The part 1 of the science project has been done by me, and the link for this is there. For the part of the science project, I have subdivided into subparts. Subpart 1 for simulation, subpart 2 for 4 simulations. So in subpart 1, I have created a C array using the time limit of 3.001 since I had run the simulation for 2000 picoseconds. So here is the extension versus time during simulation, and it is compared with the distance between the constant points, which is the straight line. And so here we can see that extension Z lags behind the C, and the distance between two constants, this is a very big lag, and so we want to reduce this. Now this is the force versus extension during the simulation. So here we can see force is always positive during extension, and also force increases with increase in extension, and decreases with a small amount after some time, after some extension. So this is the work done using work versus extension graph, and we can see as the extension is increasing, we are doing more work. So while calculating work, I use the calc1.tcl script, which calculates the work as follows. So Wt is equal to nu into integration of ft dash dt dash from 0 to t. V is the pulling velocity. So here conclusion from this graph is that if a pulling simulation is performed very slowly, then the process is reversible. The work done during such a reversible pulling is equal to the free energy difference of the system between each and final state. Now I will explain subpart 2 of the part 2 of the science project. So I have done simulation for 4 times and created a da.dat file. So each da smdtcl.out has 3 columns t, x, y, and so I have created da.dt file as follows: t1 and x coordinate for all the files first, and followed by y coordinates of all the files. So now I run the load trajectory.tcl script, which will define 3 variables: t, which contains timestamps of data, extension, which is z, and applied force f for each trajectory. So this is the extension versus time for each simulation. Each color represents a different simulation. You can see that all the extensions are overlapping with each other. Similarly, for the force versus extension, here it is similar, like we are giving the same force for extension, and here we can see it is always positive. Now for the work versus extension, the similarity is there. So this is the work done with extension. So work done to all the system should be an average higher than the PMF. Not all the work curves are higher than the PMF, and also there are some work curves lower than the PMF. Now PMF versus extension graph. So I estimated the PMF according to 3 different formulas: the original formula, the first order cumulative expansion, and the second order cumulative expansion. So this is the F1 expansion, this is the F2 expansion, and this is the FEXP expansion, which is the second order cumulative expression. So in this graph we can see this is the F1 expansion, this is the FEX expression, and this is the F2 expression, which is negative, has the F2 expression has a negative sign in front of it. So it is always be a negative quantity. So what is Jarzynski's equality? So the Jarzynski equality is an equation in statistical mechanics that relates free energy differential within two states and the irreversible work along an ensemble of trajectories joining the same state. In thermodynamics, the free energy difference delta F physical, which is Fv minus Fv between two states A and B, is connected to the work W on the system through the inequality delta F, which is less than equal to W, and equality holds only in the case of quasi-static process. In contrast to the thermodynamic statement, the Jarzynski's inequality remains valid no matter how fast the process happens. The equality itself can be straightforwardly derived from the Crookes fluctuation theorem. So the J states that this equal to this. So K is the Boltzmann constant, and using this we get this expression, and so we transfer E here, and then we do a second order cumulative to get the final FEXP expression. The scripts which I used are calc1.ecl, which is used to calculate the work at various values of x, load trajectory.tscl, which is used to calculate three variables, t which is contains the timestamp of data, z which is extension, and f which is applied force. Plot extension time.ecl is used to create plot for extension versus time using arrays f using z and t, and plot force extension.ecl used to create plot for force versus extension using arrays f and z. Also, calc2.ecl is used to find the work done for each simulation using f array, and plot w is again used for work done as each timestamps. Criminal.tcl is used to calculate the f1, f2, and fex arrays using the expression given in the Jarzynski's equality. Thank you.